Hi there and welcome to this video on Senior Physics for Electromagnetism and Electricity. In this video we're going to explore capacitors, what they do and the idea of capacitance. Okay, so the first question is, what is a capacitor? Well, basically a capacitor can be seen on the right hand side there. It's a component that can be added into a electrical circuit. Now basically what a capacitor does, it's an electrical component that stores electrical charge and then can release it over a certain amount of time. So basically charge in the form of electrons is placed into the component, and then that is delivered when there is little charge or when the power has been completely turned off. Now remember what we talked about in our introduction. When we go converting from AC to DC, we want to produce that nice flat line, and between the humps of the AC peaks, what we wanted to do is to deliver energy over a period of time while the AC got back to its peak voltage. Now it's the capacitors that have the power to do that. So firstly, just a few little points about a capacitor. This is the electrical symbol that is given for a capacitor. It's given the symbol C, and it's measured in units called farads. The symbol below in the bottom there is showing a variable capacitor, i.e. that you can change the amount of capacitance or the amount of energy which is stored in the capacitor at any one time. As I stated, that the units for capacitance are farads. However, most capacitors are measured in a lot smaller units of farads. So you get microfarads, 10 to the negative 6, nanofarads, 10 to the negative 9, or picofarads, times 10 to the negative 12. Now, it's very, very important that you understand these prefixes, because basically where you'll be given a capacitor in a scenario, you'll be expected to utilize the capacitance or the size of the capacitor and convert it into farads. So you'll be given something like a 2 microfarad, and you have to understand that that's 2 times 10 to the negative 6, or as you can see in the diagram there, 2,200 microfarad. So that's 2,200 times 10 to the negative 6 farads. So it's really important that you get a good grip of your prefixes here, because you'll be expected to utilize those in your scenarios. So here's a diagram or a slide which basically shows the different types of farads that you can have. You can see you've got your microfarads, you've got your nanofarads, you've got your picofarads. Now, just a couple of little things that you might want to know about capacitors. Often they're written with a maximum operating voltage. Obviously, that's the amount of energy that you can put as a power supply, which is going to push the charge into the capacitor. Anything greater than that, and the result is that you will damage the capacitor and it will blow up. And we'll talk about that later on. But you can see the top right-hand table shows you the various codes and the operating voltages at which they work. You can see the capacitance conversion values there. Basically, it's just telling you how you convert from one to the next. You'll have certain sized capacitors. As I said, they'll be measured in micro, nano, or picofarads. And then there'll also be a tolerance. And if you remember back to what we talked about with respect to resistance, the tolerance is basically how far as a percentage either way of the rateable value of the capacitor it happens to be. So obviously, if you've got a coded M capacitor, it's plus or minus 20%. That's 20% either side of the rated value of your capacitor. So if your rated value is 10 microfarads, it's going to be 20% above or 20% below. So there's quite a range there. Obviously, if you look at the Z, it's at 80% above and 20% below. So obviously, if you're going lower down the code, such as your Bs and Cs, you're getting to a very expensive capacitor, because it specifically will hold a specific amount of charge and won't fluctuate much around that. However, that's all well and good talking about the capacitors, but let's face it, what does the capacitor do? Remember, it stores charge, but how does it do that? Okay, well, basically, let's look at the geometry, or how it's set up first. Basically, a capacitor is 2 metal plates which are separated by an insulator. And basically how you see that they're in like a circle, how they're set up is they are basically rolled, these metal plates. Now you may say, well, if you put metal upon metal and they're two different plates, they're just going to conduct across the plates. Well, an insulator is placed in between the two plates. Now that insulator is called a dielectric. Now, different sized capacitors will work in different amounts. Basically, what you've got to work on is the metal plates will be a specific area. The bigger the area, the more charge that can actually be placed on the plates. Also, the dielectric, by putting a dielectric of different types in there, means that your insulation between the plates varies. The more insulation you've got, the better your capacitance you've got, because it can hold more charge without anything moving across. Also, the closer together you can get the plates is also and have an effect on the capacitance of the actual capacitor. So we're looking at the amount of area of metal that the charge can be placed on, the type of dielectric that you place in there, and the dielectrics can range from anything from simple paper, often they use wax paper, polyurethane, lots of different types of capacitor materials that you can use. Old days they used to use paper, but after a while they stopped using that because obviously paper, electricity, heat doesn't work too well, tend to get a few fires. But so they've gone on to more synthetic polyurethane now. So we've got the area of the plate, we've got the dielectric, we've also got the thickness of the insulatory layer. Remember, the thinner the insulatory layer, the better the capacitance. So basically we've got these two plates, and what's going to happen is charge is going to be placed on one plate, which means that charge is going to be diminished on another plate. The result is that you get a potential difference of energy from one plate to the next. Now remember, this all comes down to the principle of charges. Now if I pack electrons on one plate, remember charges are all negatively charged, they repel from each other. The more I pack onto that plate, the more repulsion I'm going to get. The more repulsion, the more energy I've got that when they want to move back to the positive plate. So bear that in mind, and I'll show you a little animation I've put together to help you try and understand that. So understand that we've got these two metal plates, dielectric, spaced apart, and they're all rolled up nice and tightly into a little component. Each terminal, each little metal which comes out of it will be attached to each individual plate, so we set up the poles of the actual capacitor. So how does it work, or what are they used for? Well, obviously it can be stored energy, and a good example of this used to be in flash photography. You used to wait for your flash to actually charge up from the battery. What you used to be able to hear was the little battery would charge up your capacitor. You'd have a capacitor linked to your light circuit. When you pressed the switch, the trigger, what would happen is an instant amount of energy would fire through the circuit, straight through the light bulb, back to the positive plate of the capacitor, and that energy would be released. Now, this is down where we use it as a time. If it's done really, really quick, we get huge amounts of energy, hence that's where you get your light from. Nowadays, it's a lot quicker, and the result is you get less charging up of your capacitor. Also, it can be used as a timing delay. So obviously, if you drip feed the water, the electricity from one plate to the next over a certain amount of time by controlling it with a resistor, the result is you can use it as a timing sequence. It can also be used as a filter for electronic circuits. So this is where we're dealing with that ripple effect. So you're delivering more energy so that you get less of a fluctuation on your signal. So you might have two or three capacitors working together to basically filter out any blips in your energy delivery. Also, it can be used as a tuning circuit. So it's used a lot linked with antennae for radio signals, and you use a capacitor to basically control and work out what signal you're getting, let's say, when you're tuning in your radio station. Okay, so this is how it basically works. Remember I said that there's two plates separated by a gap. We're going to need a power supply because the power supply is going to be the grunt that's going to push our charge from one plate onto another. Notice we've got an insulatory layer between the two plates. In this case, the insulatory layer is is air. So what happens? Well, what happens here is that the battery is going to take an electron from the right-hand plate. Here's my electron here, and it's going to move it to the opposite plate. So it's going to push it across. And then another one comes along and it pushes it across, and another. So remember, the battery is pushing this on. So what we've got is the left-hand plate is becoming negatively charged, whereas the right-hand plate is losing negative charge. Because it's losing negative charge, that right-hand plate is going to become positive. Now, for every loss of electron, we increase the positivity on the right-hand side. Remember, there's no such thing as positivity here. Really, what positivity means is there is a lack of electrons. So obviously, if the right-hand plate is going to be positively charged, it means that the left-hand plate is going to be negatively charged. Now, because it's negatively charged, what's going to happen is those particles are going to be repelling. Now, the battery will still, or the power supply will keep pushing until there's equal amounts of force pushing onto the plate, that negative plate, as there is pushing from the negative side of the battery. So eventually we'll get to a point where the force of the battery pushing onto the left-hand plate is equaled by the repulsion of the electrons from that negative plate. So as a result, the net movement in charge is zero, which means that the capacitor will now be fully charged. Now, if we then remove the power supply from this and then link it to another circuit, what will happen is that negative charge on the left-hand side will want to fly through and move to the positive plate, or where there's a lack of electrons due to the repulsive forces. By controlling the speed at which those electrons move, we'll control how quickly that energy flows. So obviously, if I put no resistor in there, it'll flow really, really quickly. I'll get a huge amount of energy, and that could be the result of a flash, for example, in a camera. Or I could drip feed it very, very slowly, and as a result, by controlling that drip feed, the result is I could use it like a timing circuit. So the principle behind how a capacitor works: the battery pushes electrons onto the one plate, and it becomes deficient on the other, becomes positively charged. As a result, when fully charged, the flow of electrons will stop when the push from the battery equals the repulsion from the negative plate. Both plates will be equally charged because imagine, if you think about it, the electrons have been removed from one plate and placed on the other. So a deficiency on this side and an excess on this side. And the PD across the plate should eventually equal the voltage of our supply. Okay, so we can look at this in the form of capacitance. Capacitance, as we know, is basically the amount of charge a capacitor can store when it's given a potential difference of 1 volt. And remember, this is measured in farads. The larger the capacitor, the more charge it contains. Okay, so if we increase the capacitor by increasing the area, for example, the result is I can put more charge on. More charge means like more electrons, which means more of a difference between the two plates. So basically we can store that greater amount of charge. As I stated, the capacitance of a capacitor will store charge. Charge is measured in coulombs on each plate when connected across a supply of volts, V. So the capacitance is basically down to the charge divided by the voltage. Now, as I've stated, capacitors have a finite voltage at which they work. If I put too much push on there, then what will happen is those electrons will actually be able to go across the dielectric and melt the dielectric. As soon as it melts the dielectric, contact is made between the two plates. As soon as the two plates are in contact, boom, we're going to get an explosion because we're going to have a massive flow of charge from one plate to the other with no resistance at all. So all that energy is just going to fly through. That's enough to produce a spark. Sparks in electrical circuits isn't a good thing. Okay, now what else can we find out about charge and capacitance? Well, if we plot a graph of Q over V, we get a straight line where the gradient in this case is capacitance. So that's where the equation actually came from, where capacitance equals Q over V. Now remember that the capacitance is basically the amount of charge required to raise the potential by 1 volt, 1 joule per coulomb. So giving 1 joule of energy per coulomb of charge. So the energy or work stored in a capacitor can be calculated by doing calculus on the graph that we basically got there and looking at the area under the curve. Basically the work can be determined by Q times V over 2, or work can be capacitance times the voltage squared over 2, or work can equal the charge squared over 2. All this has done is try to manipulate the formula and looking at the area under the curve which deals with the energy. So we can use these three equations as well as C equals Q over V to deal with a variety of looking at what the capacitance is of a capacitor and how much energy is it going to be storing. So let's look at a little example here. We've got the energy from a 1100 farad capacitor is used to operate a photographer's flash bulb. The capacitor is charged by a 9-volt battery, and we're going to calculate the energy stored in the capacitor, the energy delivered by the battery, and we're going to account for the difference in these two energies. Okay, so first off, we're going to look at the energy stored in the capacitor. Well, this is basically going to be the energy equals a half capacitance times V squared. So it's CV squared over 2, which was one of the formulae that we had in the previous slide. Well, I know what C is, I know what V is, I'm going to multiply it by 2, making sure, there's a slight slip in there, it should have been microfarads, so apologies for that. It should have been microfarads instead of just farads. It's pretty big actually, 1100 farads. But the result of that will give us 0.045 joules. Now the energy delivered by the battery, because it's only half the amount of the energy, but remember it's the area under the curve which gives us the energy. The energy which is given by the battery is going to be double the amount. So whatever I've got in A is going to be double the amount to make the full amount of energy. And finally, where's the difference? Where's it all come? Well, it's all down to heat and resistance, which is removed in the circuit. So another way that you may see capacitors actually described is like a water barrel. Water barrel can hold a certain amount of water. Once it's full, can't take any more. You can't push any back because the water will just overflow. Same sort of thing with respect to a capacitor. Also, you put a small hole in the water barrel, it will drip out really, really slowly. You put a massive hole in the water barrel, it all flows out really, really quickly. Same sort of thing when we're looking at a capacitor. We put a small drip feed of current coming out. That will be down to having a very large resistance, or I can have a very small resistance and allow it all to come out, so it will move very, very quickly. So I hope that gives you a rough idea how a capacitor works. Do have a look at some of the exercises I've put up on this post, as well as checking out the video using FET. All right, well, thank you for joining me. I look forward to you joining me again when we'll study a little bit more about capacitance. We'll look at discharging and charging of a capacitor. Thanks for watching.